another example of being able to find the area bound by two curves, we have this x squared, so our regular parabola, and then x cubed minus 3x squared plus 3x. All right, so first thing we need to do is we need to graph these functions, okay, just to kind of see what's going on. And remember in the last video, we used foo plot. Okay, so fortunately, foo plot actually defaults as x squared. In here, we have our x cubed minus 3x squared plus 3x. Now, when we graph these, I want you to notice that there's actually two different areas that need to be considered with this, right? There's this smaller area, okay, that's bound really close to the origin. But then there's also this other larger area, okay, that's right here. And it seems like that it's going to be somehow starting like maybe around 1, okay? So we can see that here. And what's really nice about foo plot is it can kind of help you to figure out what those limits of integration are. So right here, it looks like 0. Right here, it looks like 1. And then if we scroll up a lot, the last point of intersection looks like it's about 3. All right, but anyway, just going back to the original diagram. Okay, now we're going to verify those algebraically. All right, I don't want you guys to be able to just use the graphs to be able to get the points of intersection because it doesn't always work. Okay, so going back here, remember the problem says to first sketch the graph. All right, so here's our quadratic. Okay, so just regular old friendly quadratic. Imagine that it's the origin. Sorry about that. And then here is our cubic. All right, so again, not a good sketch. I apologize. All right, but these are our 3 points of intersection. One thing to also note is that the top and the bottom functions change through each of the areas. All right, so I'm going to call this one, let's just call it A1 for area 1. And then inside of the second one, let's see if I can squeeze in an A2, close enough. All right. Right here, it looks like that the cubic is the top function. Okay, so right here, this is G and then F. And then in this A2, G and F flip. Okay, so keep that in mind as you guys are going through, is that not only do you have to make sure you find your points of intersection if there are two areas, but you also have to make sure that you remember that these are probably going to flip which one's the top and which one's going to be the lower function. Points of intersection. Okay, so I'm just going to abbreviate that POI for points of intersection. That's going to be x squared equals x cubed minus 3x squared plus 3x. Anytime we have a polynomial, we set it to 0. Now we're going to factor it. Okay, and all I did here was I just subtracted the x squared from both sides. I'm going to factor out a common factor of x. Now we have a trinomial that's factorable. So it's going to be x minus 3, x minus 1. And in order of their appearance, or sequentially on the graph, the 3 solutions are x equals 0, x equals 1, and x equals 3. Okay, so that's our solution set. So right here, this is where x equals 0. Right here, this is where x equals 1. And right here, this is where x equals 3. And we need that because we need to set up 2 separate integrals. One integral is going to represent area 1. One integral is going to represent area 2. Okay, so let's start with area 1. Okay, looking at our graph, we know that the limits of integration are 0 to 1. Right? We know that g is the top function. So this time we're going to get x cubed minus 3x squared plus 3x. And the lower function is f. Okay, so all I'm doing is I'm just looking at the graph right here and seeing which one is the top and which one's the lower function. So remember the lower function is x squared and then dx. Clearly we can combine like terms right here. Okay, that's just going to be a negative 4x squared. All right, so I'll just erase this just to save room and time. Okay, so this is going to be a minus 4x squared. And now we can just integrate term by term. Right? So when we integrate, we get 1/4 x to the 4th minus 4/3 x cubed plus 3/2 x squared from 0 to 1. Now, the good news is because it's a polynomial, 0 doesn't contribute anything to the sum, okay? We should get a positive area because if we look up here, everything's above the x-axis, okay? This should be above the x-axis. That's just by poor construction of the graph. And so we're going to end up with 1/4 times 1 to the 4th minus 4/3 times 1 cubed plus 3/2 times 1 squared minus 0. If we get a common denominator of 12, 3/12 over here, common denominator of 12, 16/12, and then common denominator of 12, 18/12. All right, so 3 minus 16 is -13, -13 plus 18. This should be 5/12. Okay, of course we can use Wolfram Alpha and check our answer to make sure we've done the computation correctly. However, on examination, you're not going to have that luxury. Okay, now remember, this is just A1. Okay, so right here, if we go back all the way to the graph, A1 is going to be our 5/12. Okay, so right here are 5/12. Okay, for that area. However, we still need A2. So now we're going to flip the integral around. And remember, this time what we're going to do is we're going to have f as the top function. So for A2, the integral, we go back up, remembering that the second pair of limits of integration are 1 to 3. And we remember that this time, the quadratic is the top function, okay? And g is going to be the lower function, all right? So we're going to have x squared minus all this business, okay? So we're going to have quantity x squared minus the quantity of x cubed minus 3x squared plus 3x dx. Right? We can combine like terms. So notice we have minus a -3x squared. So that's just going to turn into a 4x squared. Let me just rewrite it because it'll be faster. So we get 1 to 3 of 4x squared minus x cubed minus 3x dx. The good news is the integration is the same as before, except the signs are going to flip around. Okay, so right here, remember we had positive 1/4 x fourth, negative 4/3, and positive 3/2 x cubed and x squared. When we integrate, this is going to be a positive 4/3 x cubed minus 1/4 x to the 4th minus 3/2 x squared. Now this time, the computations are a little more rigorous because now we have a 3 and a 1 instead of a 1 and a 0. Excuse me. So we substitute, we get 4/3 3 cubed minus 1/4 3 to the 4th minus 3/2 3 squared minus, so 4/3 1 cubed minus 4/3 times 1 to the 4th, and then we have minus 3/2 times 1 squared. All right, so what I'm going to do is I'm going to cheat and I'm going to just use Wolfram Alpha to help me out with this. All right, I could certainly use a graphing calculator. It's probably no different when you're typing these in. Okay, so I'm going to go to Wolfram Alpha. And of course, we're going to check the integrals as well when we're done. All right, so let's just evaluate our polynomial. So this is a pretty cool trick that we can do. So we can evaluate. Now remember, our polynomial, when we integrated it, was this 4/3 x to the 3rd minus 1/4 x to the 4th minus 3/2 x squared. And then we can say when x equals 3 and then x equals 1. All right, so I'm just going to type those in. So we're going to evaluate 4/3 x cubed minus 1/4 x to the 4th, and then minus, I think it was 3/2 x squared. All right, let me confirm that just by flipping back really quickly. All right, so we have 4/3, 1/4 minus 3/2. Yep. When x is equal to 1. All right, now we should get a familiar answer. Okay, so when we do that, we get negative 5/2 or 5/12, excuse me. And the reason that should be familiar is because, well, we just did it up here, except we got a positive 5/12 because all the signs were flipped around. Okay, so that's how we know, or at least in the ballpark with this. Okay, so this is just going to be a negative 5/12. And then we go back to Wolfram Alpha, and then we'll just say when x is equal to 3 this time. All right, and this time we get 9/4. All right, again, certainly we could do this with a graphing calculator. All right, so we get 9/4 minus 5/12. If we compute that, get a common denominator of 12, that's going to be 27 twelfths plus 5/12, and we get 32 twelfths, or if we could have a common factor of 4, that's going to be 8/3. All right, so now we're almost done with this. We're going to go back up here. We know that this area is now 8/3. All right, so what we're going to do to find the total area is we're just going to add our 8/3 and we're going to add our 5/12. Okay, sorry, I was doing that with the mouse. That's why it's a little bit ugly. Let me zoom back out. All right, so the total area is going to be when we take that 5/12 and we add it to 8/3. All right. If we get a common denominator of 12 once again, all right, it's going to be 32. So it should wind up being 37/12 if we've done everything correct. Okay. All right. Now, of course, what we're going to do is we're going to use Wolfram Alpha to verify this. Okay. And I know we didn't do this in the first problem. Okay. But we're going to integrate. All right. Now remember, we're going to have two different integrals, all right? And we're just making sure that we get 5/12 and 8/3, all right? Certainly we know that if we were to go ahead and add these together, because we know 32 twelfths plus 5/12 is going to be 37 twelfths, we should get that answer, all right? So remember our first integral. First integral was x cubed minus 4x squared plus 3x. And that's going to be x from 0 to 1. Okay, so if I type that in correctly, we did everything else correctly, we should end up with 5/12. I think I might have typed that in incorrectly. I think this was a plus 3x. All right, so we get 5/12. Okay, so that's good. That one's right. All right. Now we're going to integrate the same thing, but remember, all we did was we just flipped the signs. So that's nice that we just flip these around. All right. And we just go from 1 to 3. All right, and hopefully we're going to get the 8/3. We get 8/3. Now here's a really cool trick. All right, we can go ahead, just copy this, and just put the original that we had for the first one from 0 to 1. All right, and check this out. It actually gives us the 37/12 because it adds the two integrals. All right. Of course, we want to make sure we can do this by hand. And I can't stress that enough, because when it comes time for the examinations, you're not going to have access to a computer algebra system. Okay, so, but we certainly want to make sure that we're doing the steps correctly, and Wolfram Alpha can help us to at least make sure that we've gotten to the answers correctly. Okay, all right, so a little bit longer problem. Okay, and I know in the previous I didn't show you how to verify it, but at least now we know how to do the area bound by a couple curves for polynomials. Now, what if it's not a polynomial? Okay, so that's what we're going to look at in the next example.